Good afternoon. I'm Rajeev Arora, co-founder and CTO of Sensorise Digital Services. Sensorise is an M2M service provider providing IoT M2M solutions, which includes lifecycle management platforms for connectivity, devices, and analytics. We are pioneered with bringing embedded SIM in Indian market with dual profile and automatic switching of connections. So this provides a high quality of service for the connected machines, which don't know when the network goes down. So this ensures that their data keeps coming. We also provide predictive analytical solutions, and we have done for various use cases. We have done things like dynamic park pricing, and currently we are working on usage-based insurance solution using telemetry data. But today I'm going to talk about cognitive modeling approaches for learning from text. So let's move on. Agenda has the four points. We'll first review the abstract ones. We'll go through the cognitive modeling, what is cognitive modeling, and then specifically talk about three-layer cognitive model, and then take an example with topic expansion. One of the key challenges in understanding documents is to infer the context. And this manifests itself in the several forms. One of them is to learn all the possible contexts around a topic in a corpus. Feedback on room service in hospitality industry may mean different things to different people or in different regions. It could be about food in the room, amenities in the room, housekeeping or repairs in the room. In order to make an improvement, hotel needs to understand all the context. In this talk, we will discuss approach based on a three-layer cognitive model, a representation of episodic and semantic knowledge, and how these representations can be used to infer information. Text mining problem can then be stated as a hypothesis, and these hypotheses can be validated using appropriate algorithms. In this presentation, we will take the example of topic expansion to understand the concept. So let's talk about cognition and its definition. Oxford University and the dictionary provides a definition as the mental action or process of acquiring knowledge and understanding through thought, experience, and the senses. And the Cambridge Dictionary says connected with thinking or conscious mental process. If you look at further, Wikipedia expands the Oxford Dictionary further, and it says that it encompasses many aspects of intellectual functions and processes such as attention, the formation of knowledge, the memory, the working memory, judgment, the evaluation process, the reasoning process, the computation, the problem solving, decision making, and production of the language. So cognitive processes use existing knowledge and generate new knowledge. So that's the key elements in all the definitions are that there is a memory and there is a knowledge which is stored in the memory, and there is a way they are retrieved, and then there is a context around that. So let's look at what has happened in research in this area. So it started way back with memory models. So there were various memory models proposed, like Ebbinghaus in 1880 proposed a short-term and a long-term memory, which was further worked on by Atkinson and Shiffrin. And he built on that there is a short-term memory in the brain and a long-term memory in the brain. Then Larry Square in 82 came out with procedural and declarative memory, that there are two compartments. There is a procedural memory which stores the steps, and the declarative memory which stores the knowledge. While Tulving came out with a model of episodic and semantic, which say that there are episodes or experiences, and semantic is the knowledge, where the semantic knowledge is stored. Alan Newell took the procedural and declarative model and came out with the SOAR architecture. They actually took the procedural aspect of it and defined how procedural rules and procedural memory interact with each other and they work. And he provided a hypothesis around that. John Anderson came out with an ACTAR theory which worked further on SOAR and took the idea of the procedural and declarative knowledge and developed a theory about how this procedural memory and a declarative memory work together. And John Anderson says, all there is to intelligence in a simple is the simple accuracy and tuning of many small units of knowledge that in total produce complex cognition. So, according to him, this declarative knowledge or memory contains very small units of knowledges, and all these knowledge together are used in a procedural way, in some defined way, to create a cognition. And the whole is no more than the sum of its parts, but it has a lot of parts. Tulving's memory model, that is where the three-layer cognitive model is based on, says a semantic memory, which contains meanings and facts, or the knowledge itself. And this memory contains what one knows, but without any temporal dating. So it does not contain how that knowledge was acquired and when was it acquired. Okay. While episodic memory contains information about one's own experiences and when they occurred, so they are temporally dated. So three-layer cognitive model is a work further on Tulving's memory model, and it talks about that there are three layers in the brain. So every person has a linguistic layer, has an episodic layer, and an analytical layer. So linguistic layer is one which is used to make communication between two human beings. So it's a conversion layer. So it converts audio visuals into linguistic terms in the brain, or linguistic terms into audio visual, depending on which direction the communication is flowing. Right? So when an individual is communicating, then it takes the concepts from the episodic layer, converts it into terms and talk to the other person. And similarly, when a person is receiving, he converts the voice and visual inputs, converts into terms, and pass on to the episodic layer for further processing and creating the context. This layer suffers with few problems. One is called synonymy, which is the same concept but different terms. So when I say, when I requested Sachin, he assured me of his help. In this, I and me both are referring to me. And similarly, the terms Sachin, he, and his are all referring to Sachin. So there is a different terms, but the same concept. Concept is Sachin or I. Polysemy is the same term, but different concepts. So for example, we have a term Java. It can be used for programming language or refer to a coffee shop, or for an island in the country where the Java island. So a term can refer to different concepts too. And that linguistic layer cannot decipher because it doesn't have all the information. The hyponymy is the term which is contained in other term by some relation. So for example, it could be is a relation or a type of relation, like Innova is a SUV. So Innova and SUV are related and they can be used interchangeably. And they may mean the SUV or they may mean Innova. So that linguistic layer does not have the capability. Meronymy, where term which is a part of other term or concept, it's like part of relationship, like steering wheel is a part of car, and linguistic layer cannot process all these things, and they get processed in episodic layer. Episodic layer stores the experiences which it receives from the linguistic layer, okay, and it forms the concepts from those experiences. And this layer provides input for the formation of the analytical layer as well as the context for the linguistic layer. When linguistic layer wants to speak out to the other person, the episodic layer provides the context so that linguistic layer can use the right terms. Well, concepts are the higher abstraction for which are built in for each term. Analytical layer, this layer holds the concepts and the association between the concepts. So there could be many concepts which are related to each other or connected to each other, and those are being held at the analytical layer. And the concepts and their association together form the general knowledge or the fact. And these concepts are formed based on the experiences, that is episodic layers information, and they are expanded. So that's the generic concept of the three-layer cognitive model. So let us see how we can implement this in a computer domain or in a programming domain. Linguistic layer is basically nothing but a layer which will read your documents from the corpus. You have a corpus of documents. It will go through all the documents, read them, extract terms from them, and make a collection bag of terms from that document. And then depending on the language, pre-processing rules can be applied. For example, you can run a part of speech tagging, or you can eliminate stop word and then reduce the number of terms. And then you pass those terms back to the episodic layer that, okay, now you handle it. Now, episodic layer is supposed to handle concepts. Unfortunately, in the documents or linguistic layer cannot provide the concepts. So we use these terms which are received from the linguistic layer as a mental concept from the document. And then we create an association of these terms in the document, which gives us the context and abstraction of that concept. And the way the associations are done by creating a co-occurrence graph of all the terms from the document or the subset of the document. So we create a co-occurrence graph from this term set, and that forms an experience unit or the conceptual unit of that concept, what is coming out in the document. Then this episodic layer passes on this concept, that co-occurrence graph, to analytical layer, which combines all the co-occurrence graphs from the episodic layer to form a large single co-occurrence graph of corpus. So in this large co-occurrence graph, each term is represented by one node in the graph, and the edges between those two nodes defines the weight of the edge, which is in how many episodes these edges were found. Okay, so these experiences were obtained. So the weights gives us that information. So if an experience is getting embedded into analytical layer, if the same edge exists, its weights are incremented, and if the a new edge is found, then that is created. Okay. That's how the analytical layer is built. So it finally becomes a big co-occurring connected graph. How the learning process takes place in this analytical layer. So there are three steps to learn a semantic association. First is to define the semantic association in the analytical layer, and then create an hypothesis, one or more hypotheses, on how this association would exist in this analytical layer or in various episodes. Okay, so we create an hypothesis, and then we create a co-occurrence graph algorithm to extract the information based on the hypothesis, and then we validate it. So let's look at some examples like analytical association. The examples of analytical associations can be topic. Topic is, everybody knows, a topic for the document or topic for the paragraph, that what is this document about. Topical markers. Topical markers are the concepts which is most likely about another concept, but not vice versa. So for example, if we say double fault, immediately tennis comes into mind. Okay, so oh, there is a reference of tennis here. But if you say tennis, you don't think about double fault by immediately. Okay, so double fault becomes a topical marker for a tennis, right? Similarly, topic expansion. Though this is a set of concepts which collectively describe a topic term. So, if you say that, okay, I am interested in Java in the programming context, okay, then what other terms which are most likely be found when you want to search for Java for programming language? Maybe Spring Framework, maybe Hibernate. There could be many such terms. So those are the terms which are the expansion of the term Java programming in topic. So when you are searching for, let's say, Java programming, you might not, you might also want to search for a Spring Framework, for example, right? So that is topic expansion. We are trying to expand and trying to get more relevant terms. So what kind of hypothesis can be created? What is a hypothesis, first of all? So hypothesis is nothing but a co-occurrence pattern of terms which which we need to find, or which will define that topic or that particular semantic association. For example, for topic, a hypothesis could be that group of concepts that are all about the given topic or the given concept. So we need to find out, given a set of concepts, given a group of concepts, we need to find out that they are all about which one concept. So if we define a measure of aboutness, and then we find that each of these concepts which are given as an input, which are nothing but coming out from the document, they are all about a given concept, then we can say that given concept is the topic of this document. Similarly, topical markers, we can use the same aboutness measure which we talked about earlier, okay, and say that we can find that for a given concept or a term, we are interchangeably using it. Just keep in mind that for a given term, what is its aboutness to a other term, and which other term it is very highly about. And then we put a threshold that, okay, if something is above this threshold, then we will say that most likely this term is about that particular topic. So it is a topical marker of that topic. Similarly, topic expansion, and a hypothesis could be that terms relevant to the topic term, they always cluster together. Okay, or in majority of the episodes, they will be clustering together. And the term which is of interest will be part of more than, can be part of more than one topic. Like we saw example of Java programming versus Java island and Java coffee. So there are the two hypotheses, that there could be multiple clusters or multiple clusters, and each cluster will have terms which are relevant to themselves, will be clustering together. And for each of these hypotheses, we can create algorithm, a graph algorithm, or set of graph algorithm to extract those definitions. A note on the co-occurrence graph. Earlier we talked about, it's a key element. Analytical layer is nothing but a co-occurrence graph, and it is formed based on a document, which could be a paragraph or a line, or could be a book, or it could be a news article. Okay, you can define your document. Document need not be a full document. It can be a small document too. But then how do we make the co-occurrence graph? So there are three methods: distinct context, overlapping context, or co-occurrence in syntax. Distinct context is where you define it, you have defined the document, which could be an article or a chapter or a paragraph, or sometimes you may go to the line level, which I don't think ever should be, because it's too granular. And then you create clique of all terms in this document to create a co-occurrence graph. Clique is the graph where all the nodes are connected with each other. So you create the clique, and then that becomes one episode. In overlapping context, you don't use the all the terms, but you define a sliding window. Let's say we define a sliding window of plus minus 5. So totally 11 words. And you start from the first 11 words. Take those terms, make a clique. Move it one step, one word. Take the 11 words, make a clique, and append the clique with this, the previous clique, and keep on joining the cliques like this. So this way, one document will result into several cliques, and finally all the connected terms and their aggregated weights. So this will give you the more importance to the terms which are appearing closer than all the terms in the document. So that's another technique of creating overlapping context or context co-occurrence graph. Finally, the co-occurrence in syntax is that you run a preprocessor, let's say part of the speech tagger. You find out noun, verbs, adjectives, etc. And then you create pairs of syntactically connected terms, let's say noun and verb or noun and adjective. Take them as one node and then create the co-occurrence graph of all such nodes. So each node is a bipartite. So it's a bipartite co-occurrence graph where you are having one node representing a pair. It could be noun verb or noun adjective or mix of both. Okay, and then use the either the distinct approach or the overlapping context approach and create the co-occurrence graphs. So now let's see an example of topic expansion. So what's the topic expansion? It is given a topic term, find out all the topics this term could be part of. Example, Java, we have talked about it. And then find other terms or concepts which as a context for the topic. So when we say the context, let's say Java and programming context, what are the other terms which are relevant to this? Okay. Why it is useful? The applications are semantic search using query expansion. So suppose you are doing a semantic search, not just a term search, what Google does. Okay, you want to do semantic search. Okay, where you have given something like Java programming. So instead of looking for documents which are just Java and programming, you can look for documents which are like Springs and Hibernate and other things, which you will find out after expanding the Java programming and knowing that what other terms form it. Finding matching two documents, automatic tagging, various other use cases can be there. So let's look at how we can implement it in a very simplistic manner. So observational hypotheses are terms relevant to a topic term clustered together. Simple. The terms which are relevant to this topic term will cluster together. Then cluster also contains the topic term. So those clusters will contain the topic term too. And a term can refer to a different topic based on the other terms in the cluster. So you can have multiple clusters or multiple topics it can belong to. So what kind of co-occurrence algorithm we can use? 3-step cluster generation, where we can generate k cliques for n neighbors of topics. So k is the number of topics and n is the number of terms in the topic, and then we can create such cliques. Okay, so each of those cliques will be a topic of interest. But sometimes you will find that similar topics get into different cliques. So we can run an algorithm to merge the clusters and combine similar clusters into one cluster. And then finally, we can rank the terms in that cluster, each of the cluster, to form the rank order terms. And then we can pick up top n or top m terms from there as a part of topic expansion for this particular topic. Let's see an example. Let's say this is a co-occurrence graph, okay, which is made of the document. Each node and a edge defines the edge weight defines how many times this edge appeared in how many documents, and so on. So we have combined all episodes and put one analytical graph, which is like this. And our interest is to find cat, expand the cat. So we can start with cat as a topic, and we can first take its nearest neighbor, which has the highest weight, Linux. And then we say, okay, cat and Linux are connected. So we have a cluster of size 2. Then we say, okay, what else is connected with both of them? Because we are interested in cliques. And we find shell is connected with both of them. So we have a cluster of size 3. Okay, which is, and now we can't find any other node which is connected to all of them, all 3 of them. So we say that we have first cluster, which is cat, Linux, and shell. Now we go and look for the next highest edge, which was mouse, and we find the second cluster to be the cat, mouse, kitten. And if we keep on repeating, we will find 4 more clusters. Now, if you see, totally 6 clusters, but we can easily see that there are repeats, like cat, Linux, and cat, shell, and Linux are the same thing. We can combine them straight away. Similarly, cat, kitten, milk, kitten can be combined, and so forth. So we can convert them into a 4 clusters after doing the merging of clusters. But we can do a much more improved merging and say that, see, cat, Linux, shell, and cat, file, Linux have more than X amount of weight. Let's say 2/3 of the weight is common. So I will combine them too. Okay, and so I can make one cluster of cat, Linux, shell, and file, and similarly I can combine the other two, because 2/3 or based on some threshold, we can decide to combine the clusters. So it can result into 2 clusters then. So that's how you get the clusters done. Just going through iteratively going through the graph and finding out all the cliques. You can improve this much further. I have just given you the concept and the idea to move forward. You can improve it further. You can write much more evolved algorithms for both finding cliques and finding the merging the clusters. Once you have clusters, then let's say you take the cluster of cat, file, shell, and Linux. You can, using the weight, you can order them, that these are the order, cat, Linux, file, and shell. So now if I want to expand cat, maybe I will take top 2 or top 3. So cat, Linux, or cat, Linux, and file, and search for those in the documents too, to find out all semantic document relevant to cat in the Linux programming context. So that's about topic expansion and how a 3-layer cognitive modeling approach can be used to extract semantics. I know I have introduced a term called about and aboutness, and I've not explained you how to define aboutness. There are various ways of defining aboutness, and you can think of that, or we can talk offline. Primarily because we are running out of the time, and also probably our memory is getting full. Thank you very much. And if you have any questions, you can contact me at rajeev.arora@sensorise.net. Thank you.